Okay, welcome back everybody. Chapter 1, CS1 for spring semester 2023. This session is for chapter 1, so I'm going to go ahead and say CS1 spring 2023 chapter 1 notes. So in this session, we're going to go over chapter 1. I have the book in front of me, and as I mentioned in previous lectures, everything will revolve around the chapter. This chapter has no programming into it. It's mostly knowledge base. So it's information and topics that you need to be familiar with. So I have the book in front of me, open on page 1. It starts with the main topics, why we program, computer systems, hardware versus software, programs and programming languages, what is a program made of, input, processing, and output, the programming process, and then procedural versus object-oriented programming. So they start by informing you why we program, why do we need to program. Basically, computers can do many different things, many different jobs and tasks because of the fact that they are programmable. So we can program them to do those tasks, which is the power of programs. The fact that we can program it, we can customize it, we can tell it what to do, makes it very powerful. We can pick any task, any problem, any job, and program the computer to solve that problem or to finish that task. If you want to think about different ways that the people use computers, there are many things that you do even on daily basis. The average computers that you use on daily basis is not just your laptop, is not just your phone, is not just your desktop. Computers everywhere. Average computers in a car, for example, if you drove a car today, the average number of computers in a car are 30 to 40. Each car, every car has 30 to 40 computers in it. For example, in schools, we write papers, articles on a program. We send emails. We participate on online classes like right now. Right now, I'm using a computer to communicate with you, and you're using a computer to view my lecture. Even at work, people use computers to conduct business transactions. They make presentations, they control machines in manufacturing, for example, and many other tasks. Even at home, we pay bills through computers, we shop online, we do social networking, we even play games on computers, whether it's an Xbox or a PlayStation or a computer or a laptop. We want we don't want to forget MP3 players, smartphones, DVRs, car navigation systems, and many other devices. Those are also computers. So computers can do wide variety of things because they are programmed. And what is a program? A program is a set of instructions that a computer follows, right? Follows to perform a task. So you have list of instructions that are in order, and those instructions get executed in order, one instruction at a time, one instruction before the other. If the order changes, the result changes. So instruction A, then instruction B, then instruction C will produce one result, but instruction A, then instruction C, then instruction B will produce a different result. And the programs are commonly referred to as software. Anytime we say software, we mean a program. Software or programs are very essential to a computer because without a software, the computer cannot do anything. The computer doesn't know what to do without a software. And those programs or software are created by individuals, people that are known as programmers or software developers. Those people are trained and have skills necessarily to design, create, and test computer programs. So this is the section 1.1 in brief. This is what the uh, what the book is trying to tell you, and then they follow up with the fact that computer programming is both an art and science. So there is a science in it, there is engineering in it, and there is also art in it. It's an art because every aspect of a program should be very carefully designed. Also, it's an art because every programmer has different preference. For example, if I ask you right now to paint or to draw for me a landscape, your village landscape, I need your vision on houses, trees, mountains, and sun and clouds. It's very rare that two students paint the same exact paint because every developer is different, every vision is different, every approach is different. Student X will draw a paint in a vision X, student Y will draw a vision in a vision Y. The houses are going to be different, the trees are going to be different in size, different in shape, different in colors, the sun location is different, the clouds are different, but the whole scene, the whole result is the same. All students are going to provide a landscape paint, but every student will approach it differently. When it comes to computers, there are a few things that must be designed uh, in any real world program. There is a logical flow for the instructions. There are the mathematical procedures for the program. The appearance of the program, every program looks different for the user. You have the way information is presented to the user. Every program is different. Every program communicates information in a different way to the user. Then you have the program's user friendliness, how friendly it is to the user. Is it clear? Are the buttons clear? Are the tasks clear? Some software are very complicated. Some software are very easy to use. Then the last thing that is a must for any real-world computer program is the documentation and the help files. So when when you build a program or a game and you release it to the world, to the users, you have to provide some documentation. You have to provide some help files. What if I don't know what this button does? As a user, I need some documentation that tells me what each button does, how the program behaves, and the flow of the program. So this is topic 1.1. Then topic 1.2 goes into hardware versus software. Hardware versus software. So all computers as a concept consist of similar hardware devices and software component across all machines. All computers have the same set of hardware and same set of software components. So this section will provide an overview of the standard computer hardware and software organization. Again, I'm still looking at the book. So there is nothing on the screen yet, but from the book. You by now should have your book open and following up with me on the sections. Right now, I'm on page 3 on section hardware. What is a hardware? Hardware is the physical component of which a computer is made. So anything physical that you see in front of you in a computer, that's hardware. The screen, the case, the mouse, the keyboard, all those are hardware. Anything that you can touch is hardware. And the computer itself consists of major components. You have the central processing unit, which is the CPU. So I'm going to draw them here. So hardware. You have CPU, central processing unit. You have main memory. You have secondary memory. You have input devices and output devices. So if you want to think about it, you can imagine you have a box, black box. In this case, it's red box. You have the CPU, you have the memory, main memory. Then you have input devices. You have output devices. And this piece here, which is the computer, also interacts with the secondary memory. So input devices will input information to the computer, and then the computer will do some process, some task, and will produce an output. The computer, while processing, it might need to access a secondary memory. This CPU, which is the central processing unit, it's a control unit. So its job is to control and retrieve and decode program instructions in coordination with other activities of all the other parts. So this CPU will control the info coming from the input devices and will decode some instructions and execute some instructions in coordination with communicating with the main memory or the secondary memory and all other parts of computer, and finally will produce an output. Also inside the CPU, you have arithmetic and logical unit, which is ALU. This arithmetic and logical unit is a hardware, eventually, is a hardware, and it's optimized for high-speed numeric calculation. So it does the math under the hood in a very fast way. It's designed for making decisions about whether something is true or false, whether to decide for yes or no. Yes, grab from input. No, do not communicate with main. Oh, some equation produces no. Some equation produces yes. Then yes, send to the output, or no, do not send to the output. This component, ALU, is responsible for this task. So just like how you see the computer communicating with the secondary memory when necessary, there is a communication between the CPU and the ALU when necessary. Now we go to the main memory. The characteristics of a main memory: first, it is volatile. Volatile. Volatile means it loses its data. Everything stored in that memory will be lost if the electricity is gone. So the main memory is erased when the program is terminated or when the computer is turned off. You can also call the main memory RAM. RAM, which stands for random access memory. The RAM that is in your computer is the main memory, and it's volatile. Why it's random access? Because it's a big block of memory, and the CPU can access any location at any time. It doesn't have to be in order. It doesn't have to access the first slot, then the second slot, then the third slot. It's random. It can access slot number 10, then back to slot number 3, then slot number 15, etc. It can access randomly any slot in that memory. Excuse me. The RAM inside it is organized as as following. It has bits, it has bytes. A bit is the smallest piece of memory. The smallest storage unit in a computer is a bit. A bit can carry either 1 or 0. It can either carry 1 or 0 and that's it. It can't store more than one of those values. It can either store the value 1 or the value 0. 1 and 0 demonstrate or mean off or on, false or true. Imagine you have a light switch in your room. This switch can be either on or off, and that's it. It's either on or off. The byte, on the other hand, the byte is 8 bits. It's a block of memory of size 8. So 1 byte is 8, 0, or 1. For example, 1, 2, 3, 4, 5, 6, 7, 8. These 4 bits are 1 byte. And these, as a block, will be stored in memory. Bits do not have an address, but bytes do have an address. So the memory looks like something like this. It's a block of slots where each slot is a single byte and each slot has a memory address. In this case, this is address 0, this is address 1, so this is address 0 here, this is address 1 here, this is address 2 here, this is address 3, etc. This is address 8, etc. It can go as much as RAM there is in the system. If you have 16 gigabytes of RAM, then you have from 0 up to 16 giga addresses. So you have a big RAM that the CPU can store in and randomly access. The bigger the memory, the bigger the capacity of your computer in terms of running a software. If you have a big main memory, you can run multiple programs at the same time because those programs are running from the main memory. So again, as I mentioned, each byte in memory is identified by a unique number known as an address. You can't have 2 addresses with the same number. Just like house addresses, there are no 2 houses in the same city that have the same address. Every house has a unique number associated with it, and that's its address. For example, in here, address number 3 can have the number 79 in it. 79 is stored in address number 2. 113 is stored in address 6. 206, the value 206, the number 206 is stored in address number 8, and so on, so forth. Now, this value can be represented using the bit representation, which is zeros and ones. For example, we want to take the 2's complement. So 2 to power, because computers only have bits, zeros or ones, so it's two complements. It's every bit is one of two choices only. So this bit, if we want to speak about a byte, which is 8 bits, let's make it bigger. So the first bit is 2's complement power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. From 0 to 7, that's 8. 1, 2, 3, 4, 5, 6, 7, 8 bits. So let's say I want to represent the value that is stored in number 2, in address 2, 79. 79. We all know 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 2 to the power 4 is 16, and so on, so forth. 32, 64, 1, 2, 8. So, out of these values, which switch I should turn on and which switch should I turn off in order to represent the 79? The 79 consists of what? Out of these numbers, does it have 128? No, it doesn't have 128. Does it have a 64 in it? Yes, it has a 64. So 64 plus what? Plus 15. So it doesn't have 128. Yes, it has 64. So 0, 1, meaning off, on, or false, true. Now that I'm done with this, I go to the 15. The 15, does the 15 have a 32 in it? No, so off. Does the 15 have a 16 in it? No, so it's off. Does the 15 have an 8 in it? Yes, it is 8 plus 8. So, yes, it's 8. Now that I'm done with the 8, what is this consisting of? It consists of okay, by mistake I clicked to the stop record, but I'm back. We might have it two videos, but that's fine. Back to this. So the 15 is 8 plus 7. That means I have an 8. I'm done with the 8. Now to the 7. Do I have a 4 in the 7? Yes, it is 4 plus 3. So yes, I need 4. So now that I'm done with the 4, I go to the 3. Do I have a 2 in the 3? Yes, I have a 2. And since it's 2 plus 1, that means I need the 2 plus 1. So the 79 is represented using this bit representation in memory. 0, 1, 0, 0, 1, 1, 1, 1. This byte, which is 8 bits, represents the value 79 in decimal. So on the book, this section on page 3 speaks about the CPU and the history. Then they speak about the organization of a CPU, what happens inside a CPU. Then they speak about the main memory and tell you that it's volatile. Then they show you in figure 1-6 on page 6 the block of memory and how the 72 is stored in address 23, how the 149 is stored in address number 16. With that being said, about the main memory, we go to the secondary memory. So the secondary memory is what is called hard drive or hard disk in your computer. The main characteristic of a hard disk or a hard drive or a secondary memory is, unlike main memory, it's non-volatile, meaning if the program terminates, the data stored in the hard drive are not lost, do not get lost. And a hard drive, all the data in the hard drive will live in the hard drive, so that when we turn on the computer the next time, the data is still stored in the memory. So non-volatile. So first characteristic, it's non-volatile. Data will remain when the program is not running or the computer is turned off. The data can be, and the data comes in variety of media. You have a lot of different file extensions and different ways of storing them, but that's not our interest. What you need to know is you can have a magnetic hard drive or secondary memory. You can have a solid state secondary memory. You can have an optical secondary memory. You can have flash drive. So you can have magnetic. That means it's the traditional hard drive. It uses a movable mechanical arm across a disk to read and write. Another type is a solid state. So solid state, the data in solid state are stored in chips. There are no mechanical or moving parts. It's just chips inside the hard drive and the data is stored in it. You have optical. Optical means CDs, DVDs. Those are optical secondary memory. When they lose energy, right, when they lose electricity, the data is not lost, right? You can save whatever you want in a CD and take the CD out, put it on your shelf, and the data will be stored in that CD. So when you bring the CD back into the computer, you can access those data. And finally, you have flash drives. Flash drives are like USBs. Basically, they are connected using a USB port, but we call them USBs. Flash drive is a small drive that you insert into the computer and you can save data into it. When you take it off, the data is not lost. Then we go to input devices. Input devices are any devices that send information to the computer. So any device that takes an information from outside the computer to the inside of the computer is an input device. For example, mouse. A mouse takes the clicks from the user and sends it to inside of the computer. Keyboard. Keyboards are input devices. The keyboards will take the keys from the user and sends it to inside the computer. Microphone. Microphone will take the voice, converts it to digital, and send it to inside the computer. Touch screens. They are also input devices. Scanners. Scanners will send info to the inside of the computer. Cameras. A camera will take photons, converts it to digital representation, and send it to the inside of the computer. Then you have output devices. Output devices are the opposite of an input device. So we have, for example, screen. A screen, whether it's touch or not, touch screen makes it both input and output, but a screen that is not a touch screen is an output device. It grabs info or data from the computer and represent it to the user. You have a speaker. A speaker is an output device. You have printers, output devices. Anything that takes info from the computer to the outside world. Sometimes a LED light is an output device. So anything that's communicating, for example, blinking red means battery is low. Solid green means battery is full. So that's an output device. This is for hardware. Then the book wants you to know about software. Again, what is a software? It's a program. What is a program? A program is a list of instructions that are executed in order. Just like a hardware, the hardware is essential to the memory and it essential to a computer, and it's not optional. You can't have a computer without a hardware. It's not an optional component. So same works for the software. The software is not an option for a computer. You must have a software for the computer to execute. Everything a computer does, from the time you turn the power switch on until you shut the system down, is under the control of a software. The software is controlling everything the computer does. You need to know two general categories for software. You have system software. Let's go by system software. And you have application software. These are two categories, two umbrellas. The system software, you have basically the system software are programs that manage the computer hardware and the programs that run on them. For example, operating systems. Operating systems like Windows, Linux, etc., Android. Operating systems are software, but they are system software. You have utility programs, utility. Utility programs are programs that run in the background. So right now I have this program open. What else I have? So I have Zoom, I have Chrome, I have Visual Studio, but under the hood, if I open Task Manager, I go to Processes, I have Google, Visual Studio, Zoom, Windows Explorer, and there are background processes. Those are utility programs. Those are software, but they are utility. They run in the background. They are not application software. They are system software. And you have software development tools. Development tools like Visual Studio. So Visual Studio is a software development tool. So it's a software that builds or creates other software. Then you have application software. Application software are programs that provide services to the users. For example, Chrome, Office, right? Windows Office, Windows Document, Excel, etc. Games are application softwares. Any program that solves a specific problem, whether it's mathematical or else, is an application software. Then the book goes to the section for programs and programming languages. They define what a program is. You need to know what a program is. What is a program? A program, I'm hoping you are taking notes. after you read the chapter. So a program is a set of instructions that the computer follows to perform a specific task. A program, we can call it an algorithm. An algorithm is a set of well-defined steps or instructions that the computer follows to perform a task. For example, let's take an example. We want to calculate someone's gross pay. I need to build a program to calculate someone's gross pay. What are the steps? What are the steps? And they have to be in order. Can I compute before getting the values? I cannot. I have to get the values first and then compute. So the first step is what? The first step as a program is to ask the user to enter number of hours. This is the first step. Now that I have number of hours, eventually wait for the user to enter the number of hours. Once the user enters the number of hours, I need to ask the user, so again, the next step, ask the user to enter a number of pay per hour, right? Or paid, pay per hour. Now that I got number of the amount of pay per hour, I need to multiply the two. So the third step is multiply. The fourth step is display result. So this is an algorithm or a program. It's a set of well-defined instructions that have to execute in order. Can I execute step number 3 before step number 1? No, I can't. I have to get the values first and then multiply. Can I execute 4 before 3? No, I can't display a result before multiplying. I need to obtain the result first and then display. So this is what a program is. When it comes to programs, you need to know about programming languages. Now, I'm on page 9. They show you program 1-1. This is the C++ code of this program. So these are the steps, and then there is a code for it. If I get this code and put it in Visual Studio and then run the program, it will do exactly this. So we go to programming languages. Programmed and programming languages, you need to know what a machine language is. So machine language is language. Just like our language is English, machine language is zeros and ones. This is what the machine understands. The machine doesn't understand English or French or Portuguese or Spanish or Arabic. The machine understands zeros and ones. This is the machine language. And when it comes to types of languages, this is one type. You can categorize them into low level versus high level. There are high level languages and low level languages. You can imagine a human and then a machine, which is a computer in this case. So low level, high level. The closer to a human being, the language is higher. The lower to a computer, the language is low level. So a machine language is the lowest programming language. The lowest level of a programming language that exists is 0 and 1. Can a human being program using zeros and one? Yes, it can, but it's very difficult. It's very difficult for me to write zeros and ones and keep track of everything happening just by viewing zeros and ones. So the lower the language is, the difficult it is for a human. On the other hand, the higher the language is, the easier for a human. So high level languages have English in them, just like we saw in Visual Studio. C++ is a high level programming language. It has English in it. It makes it easier for me as a human. Imagine I'm typing these instructions as zeros and ones. This is the first instruction, and then I'm going to tell it, oh, this is the second instruction, right? I'm typing in low-level programming language. It's very hard for me as a human being to, to look at this code and understand it right away. On the other hand, if I look at a high-level programming language, it's easier for me to understand. Oh, include this. Oh, using namespace this. Oh, main function. Oh, hello world. Oh, system, pause, return. So it's easier because it's higher level. So you have two, low level used for communication between computers directly. So the CPU communicates with the ALU and the secondary memory using zeros and ones. They communicate between each other using zeros and ones. High level is closer to the human being, and this is how we communicate to the computers. We use high-level programming languages, and then there is a process that Visual Studio does in order to convert my Englishy text to zeros and ones so that the computer executes and understands. What are some of the popular programming languages? You have C++, you have C, you have C sharp. Those are based on each other. If I want to be accurate, you have C language, then C++, which is based on C. Then you have C plus, 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 plus. This makes it C sharp, which is based on C++. You have Java, you have Python, you have a lot of programming languages. Those are the popular ones, but there are a lot of programming languages. There are like thousands. If I bring Chrome, for example, um, how many? How many programming languages are there? 2,500 coding languages. This gives you an idea. Those are the most popular. As I mentioned, you type in C and then the Visual Studio or the compiler has a process in order to convert that language or that text into a program, into understandable instructions for the CPU to understand. That process is provided by the IDE. What is an IDE? IDE stands for Integrated Development Environment. Integrated means everything works together. Development means we use it to develop. Environment, it's an environment, it's a place where we have integrated components. We have components working with each other in order to develop. An example of an IDE is Visual Studio. Visual Studio is an IDE. It's an environment for development that has integrated components. It has editor, like I mentioned. It has a compiler. It has a debugger. It has IntelliSense. IntelliSense. IntelliSense is the tool or the component that tells you there is something wrong in your code. For example, if you see this red line and this pop-up message, this is provided by IntelliSense. IntelliSense will read my code on the fly, live, right away, and tells me, oh, this doesn't make sense. For example, oh, it's telling me, oh, this doesn't make sense. I don't understand what this means. Identifier this is undefined. It tells me, hey, something's wrong in your code. If I have something wrong in my code, I can't execute the code. It doesn't work. There were build errors. When you get this, would you like to continue and run last successful build? You can always say no. I don't want to run past versions. I want to run the version I'm looking at right now. So notice error list, it gets confused. Because of that, 1, 2, 3, 4, 5. So it gets confused. Something is wrong in your code. If I take this off, IntelliSense will detect right away that nothing is wrong with this code and will allow it to execute. So this is an IDE, Integrated Development Environment. So the IDE will take that text and will run, so text, this text will go through pre-processing phase. Then the pre-processing will go next to compiler. Then the compiler goes to linker. Then the linker will build, linker first, linker then detects other errors, when you are working with multiple files. Linker will link all things together, so it will detect if something is wrong. And finally, create executable file. The executable file is the file that you double click and it will run the program. It will execute the program. You have a figure 1-8 on page 12. It shows you from top to bottom, starting with source code, preprocessor, compiler, linker, and then executable code. Each of these steps has its own steps internally. Then we go next to the topic of what is a programmer made of. Sorry, a program, not a programmer. Program. So when I tell you a program is a set of instructions, okay, what are the possible instructions? What are the possible set of instructions? You might have what is called keywords. You might have what is called programmer defined identifiers. You have operators. You have punctuation. You have syntax. Keywords. Keywords are words that have a special meaning. Keywords may only be used for their intended purpose. You can't change the purpose of a keyword. Keywords are also known as reserved words. If I go back to Visual Studio, include is a keyword. It's reserved to the language. I can't change what include does. Include will always mean the same thing. Using will always mean the same thing. Namespace will always mean the same thing. STD will always mean the same thing in this context. In this namespace, this is what it means. Int, main, system, return. Those are reserved keywords, meaning I can't create my own ENDL word and make it mean something else. There is a list of preserved keywords, and it is on page there is a list of preserved keywords. Maybe in chapter 2 we will see it. So keywords are preserved keywords. You have a programmer-defined identifier. Programmer-defined, that means the programmer defines those identifier. The programmer can create his own placeholders, his own meaningful identifier. For example, I need an integer called my name, and this integer equals 1. I need a Boolean called this, and it is equal false. These are programmer defined identifiers. This is a keyword. Integer is an integer. 1 is 1. Boolean is Boolean. False is false. But these, I have control over these. I can call them whatever I want. So later in my program, here, for example, if I say I need an integer, let's change this to another integer and make it equal to. Now, if I say int example identifier equals this plus this, then example will become 3. This is a programmer defined that has the value 1, it's carrying the value 1. This is a programmer defined that is carrying the value 2, and I'm assigning the addition of them to this identifier or variable. Now this will become carrying 3. You have operators. Operators are just like you saw here. The plus is an operator. The equal is an operator. Equal is an operator. This is an operator, and many other operators that you will see. You have punctuation. Punctuation is just like like in English language, you have punctuations, comma, point, question mark, exclamation mark. So in the language, you also have punctuations. This is a semicolon. This indicates the end of a statement. The end of statement. So 1 statement, 2 statement, 3 statement, 4 statement. It's like instruction. First instruction, second instruction. So this indicates the end of the instruction. Notice each instruction ends in semicolon, except for functions because they have scope. So you will learn later. This is punctuation. This is punctuation. And finally, you have syntax. Syntax is the grammar of the language. Just like in English language, I can't say, in English language, it's illegal to say, I were in class. This is illegal in the English language. This is not allowed in the English language. Why? Because I is a singular, were is plural. I cannot use were plural with I the singular. So the syntax of this sentence is wrong, is broken, because this sentence doesn't meet the rule of the language or the grammar of the language. So the syntax is the rules. The syntax is the grammar of the language. So every language has its own grammar, has its own rules. In C++, in order to display the sentence "Hello World" on the screen, I have to follow this syntax. If I put one before the other, like this, now the syntax is wrong. Now I am not following the rules. So IntelliSense will tell me, hey, something is wrong. You're not meeting the syntax, and the program will not run. Same if I miss one of them. So for example, if I remove this one. So now this sentence or this statement does not meet the rule or the grammar of C++. The syntax is wrong. So again, keywords, also known as reserved words, they have a special meaning in C++, cannot be used for any other purpose. For example, the keyword using, namespace, int, float, double, return, and you will see a lot of them. You have programmer-defined identifiers, operators, punctuation, and syntax. Then you have part of programmer-defined identifiers are variables. They are variable. They are not fixed, right? They are variable. You can create them, and you have the option to put anything in them. They are variables. They can, at one point, carry 1, another point in code carry 10. They are variable. They aren't fixed. There are many different types of data, and you will learn in this course. This variable, this is a variable, holds or carries a specific data type. In this case, it's an integer. You have a lot of different data types that you will see. The variable definition, this definition specifies the type of the data that the variable can hold and the variable name. So here I'm saying this variable is called Khalil and it is of type integer. This variable is called Khalaf and is of type integer, etc. Then we go to the steps for any program. Steps for typical program. There are 3 steps: input, process, output. Any program will do these 3 steps. First, it will take some info, then it will process that info, and finally it will output a result. So it will take something, process that thing, and then produce a result. Gather data, whether from the keyboard or from a file or from the memory. Then it will process that data, and then it will produce a result. It will display a result as an output, whether display it on the screen or write it to a file or write it to a CD or save it in memory, etc. And then the final step in this chapter is telling you the difference between procedural and object-oriented programming. Back in the old days, before object-oriented programming, there was procedural programming. Procedural programming and object-oriented programming are 2 ways of thinking about software development and the design of your program. In procedural programming, the programmer constructed procedures or functions, and the procedure is a collection of statements that perform the task. So in a procedural programming, you have function A calling function B, then function B calls function C, then C calls D, and then D produces an output. It's like a chain of calls. A calls B, B calls C, C calls D, and then produce a result. It's a procedure. However, recently, like 20, 30 years ago, we started with object-oriented programming. So instead of functions calling each others, now it's objects calling each other. Objects reflect real-life situation better than procedural programming, because everything around us is objects. I am an object, the table is an object, the car is an object. Sometimes objects consist of other objects. The car is an object, it has four tires, so four objects. It has four wheels, it has one engine, it has two blinkers, two headlights, right? So one object consists of different objects. So everything is objects, and those objects interact with each other. And it's not necessary to follow a procedure like a chain in procedural programming, A, B, C, D. In object-oriented programming, an object can call object X, then call object Y, then call X, call another object. So objects are interacting with each other without a specific order or specific chain. Yeah, this is it. So I'm hoping that you read the chapter, and I need you to go over the review questions and exercises at the back. This will help you with the test, because the test is basically true, false, multiple choice from those exercises. And I will assign you the project, I will assign you the homework, and I will send you an email that module 1 is ready to be viewed. So let me know if you need help, and let me know if you have any questions.